In this video, we're going to look at empirical formula, which is part of the CC9 topic and can come up on paper 1 and on paper 2. When we're talking about formula, we're talking about the chemical formula of different molecules and compounds, which tells you how many atoms are present. There are a few different types of formula. The ones I've got written here are molecular formula, and then I've got a space for empirical formula. The molecular formula tells you exactly how many atoms are present. So for example here, I've got C4H10, which tells me I've got 4 carbons and 10 hydrogens. The next one, I've got 6 carbons and 12 hydrogens. The next one, 6 carbons, 12 hydrogens, 6 oxygens. So molecular formula is telling me exactly how many atoms of each element I have got in my compound. The empirical formula, on the other hand, is just the simplest whole number ratio. And to convert from molecular formula to empirical formula, you need to look at the numbers that you've got in your molecular formula and then divide all numbers present by the biggest number that will go in evenly. In this example, the numbers I've got are 4 and 10. The biggest number that will divide in evenly is 2. And when I divide by 2, 4 divided by 2 gives me 2, 10 divided by 2 gives me 5. I get C2H5 as my empirical formula. The next one, the numbers I've got are 6 and 12. The biggest number that will divide in evenly is 6. 6 divided by 6 is 1. 12 divided by 6 is 2. There is no need to write the 1 there. You can just write it as CH2. The next one, I've got the numbers 6, 12 and 6. The biggest number that will divide in evenly to all 3 numbers is 6. And I get CH2O. The next one, I've got C5H12. There is no number that will divide evenly into 5 and into 12, and that means that the empirical formula for C5H12 is exactly the same as the molecular formula. It cannot be simplified. Next example, I've got the numbers 3, 6 and 1. Okay, if there's no number after an element, then you have got 1. No number will divide evenly into 3, 6 and 1. 3 will divide evenly into 3 and 6. But if there's no number that divides evenly into every number present in the formula, then you are not going to be able to write an empirical formula. It will stay the same as the molecular formula. There's 4 left. I want you to press pause and do the remaining for yourself. Press play when you're ready to see the answers. So the first 3 you are just dividing across by 2. The last one, there is no number that will divide evenly into 3, 6 and 2. Therefore, the empirical formula is the same as the molecular formula. If you get asked to convert molecular formula to empirical formula, it will just be worth a mark. But they can also ask you to calculate empirical formula using mass. And if this comes up, this can be a 3 or even a 4-mark question. So this is a typical question. 10 grams of calcium reacts with 17.8 grams of chlorine. What is the empirical formula of calcium chloride? To do this, I would always start by drawing a table. And the first thing I'm going to include are the symbols for the elements present. So the symbol for calcium from my periodic table is Ca. The symbol for chlorine from my periodic table is Cl. Other things I'm going to include are mass, atomic mass, and moles. You may be wondering why I've written this as Cl instead of Cl2. Okay, chlorine is diatomic, and when chlorine is an element, it's always written as Cl2. But in this case, chlorine is not an element. Chlorine has reacted with calcium. It's part of calcium chloride. It is in a compound. And when chlorine is in a compound, it does not have to be Cl2. Because I don't know what the formula is going to be, I'm just going to write it as Cl. I'm going to start filling in my table now. The mass of calcium is given to me in the question, and that is 10 grams. The mass of chlorine is also given to me in the question, 17.8 grams. So the first row of my table is very easy to fill in. I'm getting both of those values for the question, and that will always be the case. The next line is atomic mass. This you are going to get from your periodic table. If I go to my periodic table and I look at calcium, I will see that there are 2 numbers next to it, 40 and 20. If you ever forget which number is the mass, you just look at the key. You're given this in your GCSEs, and it tells you that the top number is the relative atomic mass. So for chlorine, the top number is 40. For chlorine, calcium, the top number is 40. For chlorine, the top number is 35.5. So I'm going to fill those two numbers into my table. 40 for calcium, 35.5 for chlorine. Often the question will give you that information as well, but if it doesn't, you go to the periodic table, you take the top number. The next thing I need to do is find moles, and moles is mass divided by atomic mass. So I've got 10 divided by 40, which I'll write down for you here. 10 divided by 40 equals 0.25, and that's my moles of calcium. Then I've got chlorine, which is 17.8 divided by 35.5, and that works out as 0.5. So mass divided by atomic mass gives me moles, or top line divided by second line gives me my third line. So if you write it in this table and keep the same order, it should be very straightforward. So these are the two numbers I've got for moles, 0.25 and 0.5. These numbers represent a ratio, but to write empirical formula, I need this ratio in whole numbers. At the moment, I've got it in decimals. You might be good with numbers. You might easily be able to see what the ratio is in whole numbers. But if you can't, in order to convert these numbers to whole numbers, what we're going to do is we're going to divide by the smallest of the two numbers. 0.25 is smaller than 0.5. So I'm going to divide both of these numbers by 0.25. When I divide it by itself, I get the whole number 1. When I divide 0.5 by 0.25, I get the whole number 2. The ratio is still the same. Here, 0.25 to 0.5 is the same as what I've written here, 1:2. But now I've got it in whole numbers, and for empirical formula, it has to be in whole numbers. Easiest way to convert from decimals to whole numbers is just look at the numbers you've got, pick the smallest one, and divide everything by that smallest number. Now that I've got the ratio present in whole numbers, I can write my empirical formula. I have got 1 calcium, so that's going to be Ca, and I've got 2 chlorines, so it's going to be Cl2. And that is my empirical formula, C8Cl2. Make sure you remember to write the empirical formula at the very end. The final marks goes for writing the formula, so it's not enough to just calculate the whole number ratio. We're going to do another few examples. I'm going to use my iPad, so I've already drawn the table here. So I've got a similar question. I want the empirical formula of sodium chloride. I've written the mass of sodium chloride into my table. I've also written the formula mass of sodium and chlorine into my table. Again, those numbers I'm just getting from my periodic table. To find moles, I've written it for you here. You divide mass by atomic mass. That's going to be 4.6. 4.6 divided by 23. And that works out as 0.2. And then the other side, I've got 7.1 divided by 35.5. So it's just top line divided by second line, just like we had before. And that also works out as 0.2. Okay? In this case, both of your numbers are the same. So the ratio is going to be 1:1. Right? But if you can't spot that, you can divide both numbers by 0.2. And you get 1:1. If the ratio is 1:1, then the chemical formula is just going to be NaCl. The next example, I've got zinc reacting with chlorine. The mass of zinc from the question is 10.40. The mass of chlorine is 11.36. The atomic mass I'm taking from the periodic table. The top number for zinc is 65. The top for chlorine is 35.5. Then I'm going to do 10.40 divided by 65, and that equals 0.16. And then on the other side, I've got 11.36 divided by 35.5, and I'm getting 0.32. To simplify this to whole numbers, I'm going to divide each number by the smallest. 0.16 is smaller than 0.32. So I'm going to do 0.16 divided by 0.16 and get 1. And 0.32 divided by 0.16, and I'm going to get 2. So I end up with a ratio of 1:2. That tells me I've got 1 zinc and 2 chlorines, so my formula is going to be ZnCl2. In the next example, I have got 3 elements present, copper, sulfur, and oxygen. The masses, again, given to me in the question. So I've got 19.05 of copper. Sulfur, I've got 9.60. Oxygen, I've got 19.2. Atomic mass, I'm getting them from the periodic table. The big number from the periodic table. Then I need to find moles. It's the top line divided by the second line. 19.05 divided by 63.5 is 0.3. The next one is going to be 9.6 divided by 32. That also works out as 0.3. And the last one, 19.2 divided by 16, that works out as 1.2. Again, I've got the three numbers present as decimals. I need to convert them to whole numbers. Easiest way to do that is to divide all numbers by the smallest number. So you're going to be dividing everything by 0.3. When you do that, you get this a ratio of 1 is to 1 is to 4. The 1 corresponds to the copper, so I've got 1 Cu. The 1 corresponds to the sulfur, so I've got 1 sulfur. The 4 corresponds to the oxygen. I've got 4 oxygens, CuSO4. Now, in all of the examples I've looked at previously, when I've divided across, I've ended up with nice whole numbers. So here, when I divided across, I got 1 and 2. And here, I got 1, 1, and 4. So it's always worked out nicely as whole numbers. But that might not always be the case. And in the following example, it won't be. So in the following example, I've got percentages instead of mass. That doesn't change anything. I'm going to slot in those numbers into the top row of my table, just like I did when I had grams. So 70% iron, I just write 70% in, 70 in for the mass. And for the oxygen, I'm just writing in the 30. So I'm just replacing my grams with percentages, but it doesn't change what happens. To find my moles, it's 70 divided by 56. And I get an answer of 1.25. And for oxygen, it's going to be 30 divided by 16, and it's going to be 1.875. Now, to convert these to whole numbers, I'm going to divide by the smallest. 1.25 is smaller, so it's going to be 1.25 divided by 1.25, and that equals 1. And then 1.875 divided by 1.25, and I'm going to end up with an answer of 1.5. So I've divided across by the smallest, and I haven't ended up with whole numbers. I've got 1, which is fine, but I've also got a 1.5. If it was 1.99 that came out on your calculator, you could just round it up to 2. But when you've got 1.5, you cannot just round up or round down. But you do need to get rid of that fraction. Because it's 0.5, which is the same as a half, to make a half a whole number, you would need to multiply by 2, because 2 halves are a whole. So if I want to make this 0.5 a whole number, then I need to multiply by 2. 2 halves are a whole. But I need to keep the ratio the same. So if I'm multiplying 1.5 by 2, I also need to multiply 1 by 2. And when I do that, I get a ratio of, my new ratio is now 2 is to 3. And now I've got my ratio in whole numbers. So 1 to 1.5 is the same as 2 is to 3. I've got 2 irons, which gives me Fe2. I've got 3 oxygens, which gives me O3. Fe2O3. I've got another 4 questions which I want you to try for yourself. I haven't drawn the table, you'll have to do that for yourself, but I have given you the relative atomic masses which I've gotten from the periodic table. I've used grams in some cases, percentages in others, but it doesn't make a difference to how you do the calculation. In number 7, just be mindful, I've told you the total mass of the compound. I've told you how much is lithium, how much is carbon, but you need to find out how much is oxygen. So this is the total mass, 14.8. If there's this much lithium, this much carbon, then the rest must be oxygen. You need to figure out what the rest is and then do it exactly the same way. And then I'm pretty sure that in the last one, you're going to end up with a fraction, with a 0.5, just like we had in question 4 above. So to get rid of that 0.5 at the end, you'll need to multiply across by 2. So have a go and answering questions 5, 6, 7, and 8, and press play when you're ready to see those answers. Okay, I'm going to go through each of the answers. This is question 5. You were told you had carbon and hydrogen. I took the mass, I divided by the atomic mass, and I got the following 2 answers. To simplify this ratio into whole numbers, I divided both of them by 0.714 because that's smaller, and I got an answer of 1. It's 2.002. 2.002, you can round that down to 2, okay? It is a whole number. The ratio is 1:2, which makes my empirical formula CH2. The next one I've got carbon, hydrogen and bromine. These were the percentages given to you in the question. You use percentage the same way as you use mass. You're dividing your percentage by your formula, or by your atomic mass in each case, and you get the following answers. To simplify this, you divide across by the smallest. The smallest number here is 0.9256, so I divided everything by that, and I got the following answers. Here, you can round, okay? 2.002 is you can round it to 2. 4.008, you can round to 4, and then here, it already worked out as 1. So you get a ratio of 2:4 to 1 to whole numbers. C2H4Br is your empirical formula. The reason I kind of kept my answers here to 3 or even 4 decimal places when I did the original division is just to make it as accurate as possible here. But you should still work out with this whole number ratio. Do keep it to 3 or 4 decimal places after your initial division though, just to make sure it works out. Next one, lithium, carbon and oxygen. So you were told how much lithium you had, you were told how much carbon you had, but then you had to calculate how much oxygen you had. So you should have got 9.6 grams for oxygen. Once you know all of your masses, you're dividing all of your masses by your atomic mass, and you get 0.4, 0.2, 0.6. The smallest of these 3 numbers is 0.2. You divide everything by 0.2, and you get 2, 1, and 3. Gives you Li2, carbon, 1 carbon, and 3 oxygen. So Li2CO3. The last one, you had sodium, boron, and oxygen. You're given the percentages. You're given the atomic mass, you divide percentage by mass in each case, and you get the following 4. Again, I've kept these to 3 or 4 decimal places to keep it super accurate. Of my 3 numbers, 0.9913 is the smallest, so I divide everything by 0.9913, and I get 1, 1.998, and 3.49. Now the 1.998, I can just round that up to 2, but the 3.49, I have to leave that as 3.5, so it's still not a whole number, even with a little bit of rounding. In order to get rid of that 0.5, I need to multiply by 2. Okay, 2 halves make a whole, so I'm going to multiply by 2 to get rid of that decimal place. If I multiply 3.5 by 2 to get 7, then I have to multiply everything by 2. So it's going to be 2 by 2 to give me 4, and 1 by 2 to give me 2. So there's my ratio, 2, 4, 7. I've got 2 sodiums, I've got 4 borons, I've got 7 oxygens. That is my empirical formula. Okay, so these are typically 3-mark questions, but if you've got an extra step to do at the end, they can be 4-mark questions. Remember, your final answer comes from actually writing that formula down, so make sure you don't just stop with the calculation. Make sure you write down the actual formula at the very end.